The standard model of the Big Bang. When we talk about the Big Bang, we're talking about the beginning of the universe. Now, the universe is everything, so we're talking about the beginning of everything. So the standard model is based on this idea that our universe had a beginning. There are some key ideas to the standard model based upon the laws of physics. So the first basic idea is that our universe had to have been very small, because we know it's getting bigger, so it had to be smaller in the past, and very hot. And that's based on the gas laws, that as gas is compressed, it gets hotter. So if we compress our entire universe down to essentially a single point, it's definitely going to be very, very hot. So our graphic here is showing very, very shortly after the beginning of the universe, 10 to the negative 43 seconds after the beginning of the universe, it's going to be tiny. And 10 to the 32 degrees, it doesn't say kelvins, but this is kelvins. So very, very hot at the beginning. As the universe expands, it's going to get cooler. Again, that's based on our gas laws, that as gases expand, it gets cooler. Kind of the reverse of our previous argument there. So here, 10 to the negative 34 seconds, we've already cooled down to 10 to the 27th degrees Kelvin. Just chilly. Because it was so hot, it was too hot for matter to really exist. It was essentially radiation at the very beginning. It needs to cool for matter to form, because at such high temperatures, it's basically going to obliterate the matter. So we need to cool things down a little bit. Where did the matter come from? Well, we're back to Einstein. Einstein's the one who came up with this very famous equation, E equals mc squared. In that equation, E is energy, m is matter, or more specifically mass, and c is the speed of light, which is a big number, and then you square it, so it's an even bigger number. So what Einstein's equation told us is that, for one thing, you can take matter and turn it into energy. This is how stars shine. This is what happens in fusion processes. But you can also start with energy and create matter. It's not as easy to do, but it is possible. Because the speed of light is so big, and we're squaring it, making it that much bigger, you need a lot of energy to get matter. So, when the universe was smaller, it was also a lot hotter. which means we had a lot more energy available to convert into matter and antimatter. What is antimatter? Essentially, antimatter has the same mass but opposite charge. So for example, you can get an electron and a positron pair. So a positron has the same mass as an electron, but where an electron has a negative charge, a positron has a positive charge. Similarly, a proton and an antiproton. So we're getting this mixture of matter and antimatter as we convert energy into matter. So what are some of the general underlying ideas of the Standard Model? When we talk about the Big Bang, the creation of the universe, we're talking not just about the stuff in the universe, we're talking about the universe itself. Space is created. Einstein told us you can't have space without time, so time is created as well. So all of these things begin with the Big Bang. There is no center to the universe. There is no starting point. So when we talk about the beginning of the universe, it's everywhere. All of the universe began at the same time. Now, things have happened within it over time, so stars have formed and things like that. But the actual universe itself, all of the universe, started at the same time. So those are the key ideas when talking about the Standard Model of the Big Bang.